Hello and welcome to this manufacturing process technology part 2 module 36. We were talking about EBM machining and we were also talking about a numerical estimation through the Buckingham pi theorem of the beam matter interaction, which would lead us to a sort of a at least the governing power law with which we can relate the various parameters related to the process. So, in context of that, we had actually figured out some quantities of interest related to the functional characteristics of an E-beam process, and here the main characteristics were the beam power, which was a voltage current product, the accelerating voltage and the beam current product, the diameter of the beam d, the velocity of the beam with reference to or with respect to the workpiece. Also we were interested in the thermal conductivity of the workpiece K, the volume specific heat of the material which was being removed, which is density and specific heat product, and then we were also interested in the melting temperature and also the depth of penetration Z of the melting temperature to happen. So, with this we would like to now try to estimate some dimensional groups which are going to be non-dimensional groups. So, our functional relationship finally would be that the Z, the depth of melting temperature, is really a function of all these different parameters: the beam power, the velocity of scan, the diameter of the beam, the thermal conductivity K, the volume specific heat, which is the density specific heat capacity product, rho c, and the melting temperature theta m. So, having said that, let us try to express all these basic quantities or all these different quantities in terms of some basic dimensions like mass, length, time, temperature dimensions, and let us look at what are the effectively the basic dimensions which come out of all this different parameters. So, let us express now. So, I am just applying Buckingham pi theorem here. So, let us express all quantities represented in the last functional relationship of the depth of melting temperature Z in terms of basic units or basic dimensions M is for mass, L is length, T is time units and theta is temperature units. So, for example, if we look at power is nothing but its force velocity product. So, you have mLt minus 2 as the basic unit for force, mass acceleration product times of the velocity L t minus 1. So, therefore, this basic representation of power would be in terms of mL t minus 3. Similarly, velocity v is L t minus 1, diameter again is a length unit. So, you have L, and the dimensional representation of thermal conductivity K is given by mL t minus 3 theta minus 1, and just wanted to make sure that these things do not interfere. So, minus 1, and then we have the volume specific heat rho c product, which is ml minus 1 t minus 2 theta minus 1, and theta m is again theta, Z basically is the length L. Okay. So, these are the basic representations of all these different parameters that we have pointed out in the last step in terms of basic dimensions, that is the mass, length, time and temperature dimensions. I am not going into details of each and every one of these because these are very elementary how you have arrived at them, and let us now see what the Buckingham pi theorem has to say. So, according to the Buckingham's pi theorem, we can form exactly n minus m non-dimensional groups by taking into account all parameters of the experiment. Okay. So, in this particular case there are about 7 different parameters, as you can see here. So, n is the number of, okay, so let me just comment about n and m here. So, n is the number of different parameters and m is the number of basic dimensions where all these parameters are being represented. So, you have 7 different parameters here: power, velocity, diameter of beam, thermal conductivity, the specific heat volume specific heat capacity, and temperature theta, and z being the depth of melting temperature. So, there are about 7 different basic parameters related to the experimental process, and you are representing them in terms of 4 basic dimensions, that is the mass, length, time and temperature dimensions. So, you can exactly have 3 groups here, right. So, n minus m non-dimensional groups can be taken into account or can be formulated. Okay. So, let us now look at in our case n equal to 7, number of parameters, m equal to 4. So, you have n minus m equal to 3. So, you have 3 non-dimensional groups, and the idea is that all these groups, if formulated, they should be able to represent themselves in terms of one another, so that ultimately we can get at least a power law relationship between the basic dimensions. So, here for example, if we were to introduce 3 different groups, let us say we try to formulate group pi 1, which is again non-dimensional, and we will somehow see how to do or how to make it non-dimensional. So, let us assume these groups to be linearly related, in one case to the depth of melting temperature z, another case maybe to the beam diameter, and third in to the depth of or to the melting temperature of the material. Okay. So, in one case let us assume a non-dimensional group pi 1 being formulated by the other different parameters which are mostly involved apart from the z, d and theta m. So, apart from these 3 parameters, the other parameters which are involved in all the analysis are the power p, the velocity of the beam v, thermal conductivity k, and the volume specific heat capacity rho c. So, these are the basic 3 dimensions where there are linearization of the power of these with respect to the non-dimensional groups, and let us assume that we have a coefficient, or we define a coefficient alpha, beta and gamma, where the subscript changes between alpha 1, beta 1, gamma 1, alpha 2, beta 2 and gamma 2, and alpha 3, beta 3 and gamma 3 between the 3 non-dimensional groups here. So, the first one has a linear power of z times of p to the power of alpha 1, v to the power of beta 1, k to the power of gamma 1, rho c to the power of delta 1, okay, such that the group pi 1 has exactly 0 dimensions. So, I am just trying to linearize in terms of one of the parameters, okay, and I am trying to make groups for all these 3 different parameters where they go linearly into each group, the z, d and theta m, which they go linearly into each of these non-dimensional groups, and the other 4 parameters which are left over apart from the parameters which are linear in these 3 non-dimensional groups are to be raised to certain powers, so that ultimately the group has 0 dimensions. Similarly, in the case of the second equation, we have p to the power of alpha 2, v to the power of beta 2, k to the power of gamma 2, rho c to the power of delta 2, and the third case which goes linear in theta m, we have p to the power of alpha 3, v to the power of beta 3, k to the power of gamma 3, rho c to the power of delta 3, and that is how the Buckingham pi theorem is applied. So, we need now to calculate everything in terms of basic dimensions. Remember, basic dimensions are 4, that is mass, length, time and theta, and try to find out what are the values related to alpha 1, beta 1, gamma 1, delta 1, and similarly in all the all the equations is alpha 2, beta 2, gamma 2 and delta 2, and alpha 3, beta 3, gamma 3 and delta 3. So, substituting the dimensions of each quantity, we equate to 0 the ultimate exponent of each basic dimension I already mentioned that pi i's are non-dimensional groups or non-dimensional numbers. Okay. So, let us look at what happens to individually these equations. Okay. So, we have, for example, in the first case pi 1 case, we have z times of p to the power alpha 1, v to the power of beta 1, k to the power of gamma 1, rho c to the power of delta 1. This comes as dimension L times of dimension for power, which is m L 2 t minus 3 as borrowed from earlier to the power alpha 1, plus dimensions of velocity L t minus 1 to the power of beta 1, plus that of thermal conductivity, which is m L t minus 3 theta minus 1 to the power of gamma 1 times of this rho c, the volume specific heat capacity to the power delta 1, and this volume specific heat capacity was represented in terms of dimensions sorry, m L minus 1 t minus 2 theta minus 1 to the power of delta 1. So, if I were to assemble all the different basic dimensions together in this algebraically, we will be getting m to the power of alpha 1 plus gamma 1 plus delta 1. Okay. We get L to the power of 1 plus twice alpha 1 plus beta 1 plus gamma 1 plus or minus delta 1, because it is ml minus 1 in this particular case, in the last group's case. So, minus delta 1, and then we have time units t to the power of minus 3 alpha 1 minus beta 1 minus 3 gamma 1 minus twice delta 1, and then temperature units which are minus of gamma 1 and minus delta 1. And so, all of these are equal to m to the power 0, L to the power 0, T to the power 0 and theta to the power 0. Remember, the group, the whole group as such has basic dimensions 0. It is a dimensionless group that we are talking about. So, we are left with 4 linear equations here, where alpha 1 plus gamma 1 plus delta 1 is 0, and twice alpha 1 plus beta 1 plus gamma 1 minus delta 1 becomes equal to minus 1, and minus 3 alpha 1 minus beta 1 minus 3 gamma 1 minus twice delta 1 is equal to 0, minus gamma 1 minus delta 1 is equal to 0. So, these are set of 4 equations, linear equations with 4 variables, which can be easily solved, and we are left with so solving these, we are left with alpha 1 equal to 0, beta 1 equals 1, gamma 1 is minus 1 and delta 1 is equal to 1. You could actually substitute this back and put, or maybe solve using Gauss elimination or just normal substitution method, and you could actually be able to get the different values of alpha 1, beta 1, gamma 1 and delta 1. So, if I were to put all these values back into the pi 1, which was initially assumed to be a non-dimensional group, the pi 1 thus would come out to be z v rho c k with the value of alpha 1 equal to 0, beta equal to 1, gamma 1 equal to -1 and delta 1 equal to -1. We do similar solutions for pi 2 and pi 3 groups, and in case, and I am not going into the details of the calculation here, you are welcome to do it yourself in the same manner that I did for pi 1. Okay. So, pi 2 becomes equal to dv rho c by k, and pi 3 becomes equal to in this case k square theta m by rho c v times of power p. So, these are the three groups that are being formulated. Obviously, you can think of the similarity between pi 1 and pi 2 because both of them had a linear dimension in length. One was indicating the depth of melting temperature z, another was indicating the diameter of the beam. Both are length dimensions, and length dimensions were going linearly. So, obviously, the other portion of the group would be similar in terms of their alpha, beta, gamma and delta values. For pi 3, it is slightly different because we are now talking about temperature as a basic variant which goes linearly into the pi 3, and therefore, k square theta m by rho p times of rho c volume specific heat times of the velocity at which the beam can be rastered. Okay. So, that is how all the three coefficients pi 1, pi 2 and pi 3 are related. And let us say now, assuming again further along the way, let us say we get a functional relationship between pi 1, pi 2 and pi 3, as pi 1 is a function of, let us say, pi 2 and pi 3. Now, this could be either way. It could be pi 2 as a function of pi 1, pi 3, or pi 3 as a function of pi 1, pi 2. The only thing which would happen here is that we have to somehow be able to correlate only on the dimension front, that it should be consistent. So, you have pi 1 which is a non-dimensional number as a function of two more non-dimensional numbers. So, dimensionally they are absolutely consistent, and there is no question in this particular presumption. And pi 1 already was a group which was having rho z v rho c by k, and this would be a function of pi 2 which is a group d v rho c k, and pi 3 which is a group k square theta m by p rho c v. Okay. So, that is how the functional relationship would actually exist. And now we try to see what we have in terms of experimental or empirical information from the experiments, and we have that z is found out empirically to be proportional. So, this empirical happens from experiments obviously. So, you can say that this knowledge is borrowed from all experiments to be proportional to. So, this is more from a regression analysis point of view, proportional to the power p. Okay. So, as the p increases, the depth of melting temperature z also increases. So, therefore, if we had this kind of a relationship which is linear in power, we may as well have to revert back the presumption here which says that this was inverse, the z was inversely proportional to the power. So, we can actually write the relationship here as z rho v c by k equals this rho v c times of power by k square theta m, and a function of, let us say, dv rho c by k. It is no harm because again this group is absolutely 0 dimensional. So, if it is even the inverse of this group, or the group directly, both of them have no dimensions, and the dimensional consistency in this equation still holds even if it is the inverse. Okay. But here we are getting though a closeness to the empirical estimation determined from the experiment which says z is proportional to the power, and that is something that will be important here for the prediction of this whole formulation. So, therefore, we have now, if I just wanted to cancel a few terms here, we are having, or we are left with a new relationship Z k theta m by power p is a function of Z v rho c by k. Okay. And now you can actually have a predetermined experiment. So, experimentally one can observe that the actual Z k theta m by power p is nothing but 0.1 times of d v rho c by k times of minus to the power of minus 0.5. So, this is a completely regressional experimental empirical relationship that you may say, and what essentially it brings us to that we are maintaining dimensional consistency to arrive at a final formulation which we are now empirically investigating whether there is a relationship between the parameter which has been formulated here and the parameter which has been formulated here. So, such a relationship exists, and so therefore, we can say that actually the Z value comes out to be 0.1 times the power value divided by theta m times of root of k d v rho c. Okay. So, you can just sort of because there is a k term here, you bring the k, this is k to the power of 0.5. So, this root k v d rho c comes through that method, and so Z is inversely proportional to the melting temperature, which is a very good to go assumption. Obviously, if the melting point is higher, the amount of depth of penetration of the beam would be lower, and so is the power. If the power is higher, the depth of penetration Z is again higher. So, from the two empirical relationships, you can already observe the power of this technique, that we could arrive at an actual formulation using a non-dimensional analysis, where all these different parameters, the velocity, the volume, heat capacity, the conductivity of the material, the beam diameter, the depth of melting temperature Z, the melting temperature itself theta m, and power could all be correlated to arrive at some ballpark relationship which would be more accurate in processes related to e-beam machining. Let us just look at the same experiment that we had conducted earlier numerically and arrived at some velocity. In that case, it was I think about 4.6 centimeter per second that we had arrived at in probably one of the modules, where we were talking about the velocity of scan of a particular e-beam. In this case, the velocity actually obtained through this empirical analysis is much semi-empirical analysis is much higher, as you will see. So, let us go back to the earlier problem, where from the guesstimate relationship between power and the material removal rate. Remember, power was in watts, and this Q value was taken to be millimeter cube per minute, and the C values were all estimated empirically. We had for a 150 micron wide slot of 1 mm thick tungsten sheet, and with an electron machining, beam machining carried out at 5 kilowatt power, we had a speed estimate of about close to 4.6 centimeters per second. Okay. By this relationship, this guesstimate relationship P equal to CQ. Let us look at our new formulated relationship here, and for tungsten, for example, the value of volume specific heat can be estimated rho c to be 2.71 joule per centimeter cube degrees Celsius. The thermal conductivity K for the tungsten can again be estimated at 2.15 watts per centimeter degrees Celsius. The melting temperature theta m for tungsten is about very high, 3400 degrees Celsius, and we get that the Z value therefore in this case is 1 mm, okay, because the beam has to penetrate through the thickness of the tungsten sheet, 0.1 centimeters, and the diameter of the beam obviously should be equal to the slot width equals slot width, and in this case the beam diameter for that to happen should be about 150 50 microns, about 0.015 centimeters. Power of course is 5 kilowatts, so 5000 watts, and you know, the velocity arrived at, therefore from the relationship z is equal to 0.1 p by theta m root over k d v rho c is around 24.7 centimeter per second. So, it is about 6 times higher, as you can see, 6 times higher than what was predicted by the guesstimate, you know, with the different c values. So, this is a more appropriate expression that you know, that actually leads to prediction of the cutting speed or cutting velocity of an e-beam system. So, I think I will sort of close on this module here, and you know, in the next few modules we will discuss about a little bit about, you know, the effects of e-beams on various materials, and then probably start another topic of interest, which is the laser beam machining system. So, with this I will close this particular module. Thank you, and thank you for being with me. Bye bye.